Hello everyone. In this video, we are going to discuss more number of worked examples based on some degrees vertices theorem. Okay. Now let me see this first problem. They clearly mention that GB is simple graph with 11 vertices. 11 vertices. Let me write that point. The number of vertices in the graph they provided 11. There are 11 vertices are there. And if degree of each vertex is at least 3, so whenever they mention at least 3, that indicates minimum degree among all vertices. But we know that minimum degree among all vertices is denoted by small delta of G. Minimum degree among all vertices denoted by small delta of G, which is equals to 3. Okay. And at most 5. At most indicates maximum degree of all vertices. Maximum degree among all vertices denoted by capital delta of G. That equals to 5. Then the number of edges in G should lies between dash and dash. So they're asking the range for number of edges. Okay, so we want to fill up these two blanks. So that is actual meaning of this question. Now you please recall there is a relation between minimum degree and number of edges, and there is a relation between maximum degree and number of edges. What is that relation? That relation is small delta of G always less than or equals to average degree of a text. But what is the meaning of average degree of a text? Average degree of a text means sum of degrees of all vertices by total number of vertices. Sum of degrees of all vertices by total number of vertices. But sum of degrees of all vertices is equals to 2 times of number of edges by using sum degrees vertices theorem. Okay. So therefore, it is 2 times of number of edges by total number of vertices means number of vertices. Okay. Which is less than or equals to maximum degree of all vertices, that equals to capital delta of G. Right? Okay. Now substitute all these values, which implies that small delta of G is equals to 3, less than or equals to 2 times of number of edges. So here we want to find number of edges. And number of vertices is equals to 11, less than or equals to 5. By multiplying with 11 for the total inequality, we'll get 33 is less than or equals to 2 into number of edges less than or equals to 55. Just multiply with 11 for the total inequality. Okay. Afterwards, divide with 2 on both sides, we'll get number of edges. That is 33 by 2, which equals 16.5. Less than or equals to number of edges less than or equals to 27.5. 27.5. Now I want to choose E value which satisfies these two conditions. But what kind of values you have to choose? Minimum value of E and maximum value of E. Okay. So in this inequality, the minimum value of E is equals to min value of cardinality of E is equals to. What is that minimum value? That equals to 17. Right? And max value of E is equals to which satisfies above condition, which is 27. Okay. So therefore, minimum value is 17 and maximum value is 27. The correct answer for this question is B is the correct answer. Right? So you can expect questions like this, where this problem based on minimum degree of vertices and maximum degree of vertices. Okay. I hope you understood this problem, right? Let me go for second problem. So now look at second problem. A simple graph is called regular. A simple graph is called regular if all its vertices have the same degree. I remember in the last video I explained what is the meaning of regular graph. In a graph, if every vertex having same degree, then it is called simple graph, right? Sorry, in a graph, every vertex having same degree, that is called regular graph. Okay. So in this example, a simple graph is called regular if all its vertices have the same degree. Let G be a connected regular graph with 22 edges. Okay. So they clearly mention that number of edges are 22. Number of edges are 22. And what type of graph G? G be a connected graph, connected simple graph. Okay. And it is given that G is connected simple regular graph. G satisfies these three conditions: connected simple regular graph. Okay. Connected means it must have minimum n minus 1 edges. It must have minimum n minus 1 edges where n indicates number of vertices. Okay. Simple means no self loops, no parallel edges. Regular means degree of every vertex is same. So here a possible number of vertices in G. They're asking a possible number of vertices in G. So what is the cardinality of V? Possible number of vertices in G. Okay. Suppose I am assuming that G is K regular. Assume that G is K regular. If it is K regular, then K into total number of vertices must be equals to 2 times of number of edges by using sum degrees vertices theorem. Sum degrees vertices theorem says that sum of degrees of all vertices must be equal to 2 times of number of edges. So clearly we are having V number of vertices and each vertex having degree K, therefore K into V equal to 2 times of edges. Okay. From this, cardinality of E is equals to 2 times of number of edges by K like this. Therefore, cardinality of E is equals to E indicates here total number of edges, which is equal to 22. So 22 by 22 into 2, which is equal to 44. 44 by K. Clear? Because E they mentioned it is 22. Please look at here. E value equal to 22. Therefore, 2 into 22 44 by K. But remember, total number of vertices must be integer. We cannot take fractional values. Therefore, what are the possible values of K here? K could be, in order to get integer, K must be divisor of 44. That is, it may be 1, or it may be 2, it may be 4, or it may be 11, or 22, or 44. These are possible values of K. Okay. Now we want to eliminate some values now. Okay. Suppose if K equal to 1, then what about V? Total number of vertices 44. Total number of vertices 44. But is it possible to have total number of vertices 44? Is it possible to have total number of vertices 44? Let me write that point. Suppose if K equals to 1, then cardinality of E is equals to 44 by 1, which equal 44. It is not possible. It is not possible to have 44 vertices. How can I say it is not possible? Because in a simple connected graph, if we have 44 vertices, it must have 43 edges. It must have minimum 43 edges. Okay. Repeating once again, in a simple connected graph with 44 vertices, it must have minimum 43 edges. But how many edges we had in this problem? Only 22 edges. 22 edges. Okay. So therefore, cardinality of equal 20, 44 not possible. I'm repeating this sentence once again. Suppose if cardinality of E equal to 44, then what is the problem? If cardinality of E equal to 44, in order to ensure that the graph is connected, the number of edges minimum 44 minus 1, that equals to 43. Clear? So, but here how many edges we have? 22. Therefore, K equal to 1, V equal to 44 is not possible. Then suppose if I take K equal to 2, K equal to 2, then cardinality of E is equals to, substitute K equal to here, 44 by 2, that equals 22. If number of vertices are 22, minimum number of edges to ensure that the graph is connected are 21 edges. 21 edges. But how many edges we have? 22 edges. Obviously, this condition is satisfied. Okay. Therefore, it is possible. It is possible. Okay. Suppose assume that if it is possible, suppose let us assume that it is possible now. Okay, k equal to, then cardinality of equal 22. But they clearly mention that it is a regular graph. Regular graph. Correct? Regular graph. Suppose if k equal to regular graph, k equal to means two regular graph. In two regular graph, 2 into v is equals to 2 times of edges, which is satisfied. Therefore, both the conditions satisfied, I can say it is possible. Okay. Next, if I take k is equals to 3, sorry, k equals to, next one is 4. Then cardinality of e is equals to 44 by 4. Please look at here, 44 by 4, that equals to 11. If the total number of vertices are 11 means, in order to ensure the graph is connected, we must have 10 edges. Obviously, we have more than 10 edges. Therefore, there is no problem with this. Okay, which is also possible. Also possible. Okay. Next. Now, suppose if I take k equals to 11, then total number of vertices is equals to 44 by 11, that equal to 4. But remember, if v equals to 4, then it is not a simple graph because it is having 22 edges. Okay. If v is equal to 4, please listen this explanation once again. If v is equals to 4 vertices, then minimum number of edges must be 4 minus 1, 3. 4 minus 1, 3. And the max number of edges, it must be n into n minus 1 by 2 condition. N into n minus 2 means 4 into 4 minus 2 by 2. That equals to 6 edges only possible maximum. But how many edges they mention here? 22 edges. 22 edges. Repeating once again. Then v equal to 4, which is not possible. Not possible. Why it is not possible? If v equal to 3, then cardinality of v minimum must be v minus 1 and maximum is equals to v into v minus 1 by 2. Max number of edges are n into n minus 1 by 2. Minimum number of edges are n minus 1. Okay. Which equal to 3 less than or equals to e less than or equals to, which is 6. Right? Means maximum 6 edges only allowed. But how many edges they provided here? Please look at here how many edges they provided. 22 edges. Therefore, if k equal to 11, v equal to 4 is not possible. Similarly, if v equal to 4 not possible means obviously for k equal to 22, v equal to 2 is not possible. And k equal to 44, v equal to 1 not possible. Therefore, what are the possibilities are there for number of vertices? Number of vertices may be 22 possible and 11 also possible. But in the option they provided 11, so I can say the correct answer for this question is 11 is the correct answer. Right? So this is a problem which is based on regular graph. Okay. Is it clear? So two problems were completed. Now let me see third problem. Look at third problem. Let G, if G be a simple graph of 38 edges. So they clearly mention that number of edges in the graph 38 edges. Number of edges in the graph 38 edges. And degree of each vertex is 4. If degree of each vertex is 4 means that is equal to k regular graph. Sorry, 4 regular graph, right? Okay. And we know the relation in k regular graph, it must satisfy the condition k into number of vertices equals to 2 into number of edges. Where k means here 4 regular graph. Therefore, 4 into number of vertices equals to 2 times of number of edges, that equal to 38. Okay. From this total number of vertices equals to 19. Okay. So therefore, answer to this question is 19. Right? Now see problem number 4. Look at this problem number 4. Suppose all vertices in a graph G have degree k, where k is an odd number. The number of edges in the graph G. Okay. Now, by using sum degrees vertices theorem, summation I runs from 1 to n degree of all vertices is equals to 2 times of total number of edges, right? Total number of edges. Where n indicates here, where n indicates cardinality of E, means total number of vertices are n. Total number of vertices are n. Okay. So the claim means that suppose all vertices in a graph G have degree k, degree k. So every vertex having degree k, therefore this total V1 is having degree k, V2 is having degree k, like that each and every vertex having degree k. Therefore, if I expand this total part, how many k's will be added? N k will be added. Therefore, this total indicates n into k is equals to 2 times of number of edges. Okay, because we have total number of vertices are n. We can also write n as cardinality of V into k is equals to 2 times of number of edges. Number of edges. Now they're asking the number of edges in G. Therefore, number of edges in G is equals to k into number of vertices by 2. Okay. It means that number of edges always is equals to k into something. This part is something an integer. K into something. Okay. So k into something is nothing but we can say multiple of k. Okay. It is nothing but it is multiple of k. Therefore, the correct answer for this question is option C is the correct answer. Okay. Now see question number 5. Which of the following degree sequences represents a simple non-directed graph? Non-directed means it's nothing but undirected graph. Okay. So in order to answer this question, you please recall standard properties which we covered in a previous class. Okay. So let me write quickly those properties so that you can understand quickly. The first one is in a simple graph, with n vertices, a simple graph with n vertices, in a simple graph with n vertices, maximum degree of any vertex is n minus 1. Please remember that. Because if it is having more than n minus 1, obviously it is not a simple graph. Okay, the simple basic concept, please understand. In a simple graph with in a simple graph with n vertices, if any vertex is having more than, if any vertex is having degree more than n minus 1, obviously there is a self loop or parallel edges are possible. Then it is not a simple graph. Okay, therefore, in a simple graph with n vertices, maximum degree of any vertex is n minus 1 only. Maximum degree of any vertex is n minus 1. That is at most n minus 1. Okay. Degree of any vertex is at most n minus 1. That is degree of any vertex at most n minus 1. This is the first point you have to remember to answer this type of questions. Okay. This is the first property. Please remember the first property. And the second property, in a simple graph with n vertices, simple graph with n vertices, if two vertices are having degree n minus 1, if two vertices are having degree n minus 1, then there does not exist a vertex whose degree is whose degrees either 1 or 0. So what does it mean? Suppose, for example, I have a graph with n vertices. In that graph, if two vertices are having degree n minus 1, like vertex 1 is connected to remaining all n minus 1 vertices, then I can say vertex 1 is having degree n minus 1. Similarly, vertex 2 also connected to remaining n minus 1 vertices. Then I can say degree of vertex 2 also n minus 1. If I have two vertices of degree n minus 1, then definitely I cannot find a vertex whose degree is 1, because that vertex is adjacent to either v1 or v2, right? Adjacent to both v1 and v2. Therefore, we cannot find a vertex of degree 1, or we cannot find a vertex of degree 0 also. Okay. So, in a simple understanding point of view, just observe this example. Suppose I have a vertex v1 and v2, v3, up to so on vn. There are n vertices are there. And if I write the degree sequence, assume these are vertices and a degree sequence. Suppose v1 is having degree n minus 1. What does it mean? v1 is connected to remaining all other vertices. Is it correct or not? So it is looking like this. v1 is connected to v2, v1 is connected to v3, and v1 also connected to vn. Then I can say degree of v1 is equal to n minus 1. Okay. Similarly, degree of v2 also n minus 1. It means that v2 connected to, let me write with a different color, v2 connected to v1, v2 connected to v3, v2 also connected to vn, like this. It is connected to every other vertex. In that case, we cannot find a vertex whose degree is 1 or 0. The reason is v1 is already connected to that vertex, v2 also connected to that vertex. Therefore, minimum degree must be 2 only. We cannot get a vertex of degree 1 or 0. I hope it is very clear, right? Okay, you remember this point also. Okay. Next, the third important point you have to remember: in a simple connected graph, or in a simple graph, with n vertices, if each vertex having degree n minus 1, then we'll get max number of edges in that graph. Okay. And what does it mean? Suppose, tell me, according to first property, in a simple graph, please look at first property. In a simple graph with n vertices, please look at here. In a simple graph with n vertices, maximum degree of any vertex is how much? N minus 1. Maximum degree of any vertex is n minus 1, right? Like that, suppose every vertex having maximum degree. Like that, first vertex is having n minus 1, second vertex also having degree n minus 1, like the nth vertex also having degree n minus 1. Let me that point. That is, its meaning is, that is v1, v2, v3 up to so on vn. There are n vertices are there. Okay. Where degree of v1, how much they are saying? N minus 1 is the degree of v1, and degree of v2 also n minus 1. Degree of V3 also n minus 1. Degree of Vn also n minus 1. Clear? Like that, we are having degree of each and every vertex. But if I sum up degrees of all vertices, the sum of all these degrees, this total value must be equals to 2 times of total number of edges according to some degrees of vertices theorem. Okay. So some degrees, according to some degrees of vertices theorem, it must be total number of 2 times of total number of edges. Okay. So total how many times n minus 1 we are having? N times we are having n minus 1. Therefore, total we are having n times of n minus 1. Therefore, n into n minus 1 must be equal to 2 times of number of edges. Therefore, number of edges are n into n minus 1 by 2. Means, please remember this important point. In a simple graph, if every vertex is having degree is n minus 1, then maximum number of edges are possible in that graph. Okay. So these three important points are useful in order to answer this type of question. Okay. Now look at first problem. Which of the following degree sequence represents simple undirected graph? Okay. Now look at this one. Total 1, 2, 3, 4, 5, 6. 6. There are 6 vertices are there. First, we'll verify our fundamental theorem. What is that handshaking lemma? Handshaking lemma says that sum of degrees of all vertices must be even number, right? We know that sum of degrees of all vertices sum of degrees of all vertices must be 2 times of number of edges. 2 times of anything is nothing but it is even number. Please remember that point. 2 times of anything is nothing but is even number here. Okay. If you take sum of all these degrees, just sum up all these values now. We are having 2 plus 3 plus 3 plus 4 plus 4 plus 5, which is equals to 6, 10, 14, 19, 21, which is not equal to even number, right? It's not equal to even number. Hence, the first sequence does not represent a graph. First sequence does not represent a graph. Okay. Remember, the sum degrees vertices theorem is applicable for any type of graph, whether it is simple or multi-graph. For any graph, it is applicable. Okay. So clearly, sum degrees of vertices theorem is not verified. Therefore, the given degree sequence is not a valid sequence for the given graph. Let me check next one. There are total 5 vertices are there. The total 5 vertices are there. And tell me, if we have 5 vertices, what is the maximum degree of any vertex is possible according to rule number 1? According to rule number 1, please look at rule number 1. According to rule number 1, in a simple graph with n vertices, maximum degree of any vertex is n minus 1 only. But if you observe here, I can find a vertex whose degree is more than n minus 1. Okay, which is against to the rule number 1. I can say the rule number 1. Please remember. Okay, rule 1. And you can call it as rule number 2, which is rule number 3. Okay, so I cannot find a vertex of degree 5. Therefore, it is not a valid sequence. Quick repetition. If a graph contains 5 vertices, I can find a maximum degree of any vertex is only at most 4. We cannot find 5 by using rule number 1. Okay. Next, look at this one. Rule number, third problem. 1, 2, 3, 4, 5, 6, 7. 7 vertices are there. If there are 7 vertices, maximum degree of any vertex is at most 6. Yes, we have only 6. We have only 6. That condition is okay. And if you sum up all the vertices, it must be equal to even number. Let me sum up all the degrees of vertices. 6 plus 6, 12, 17, plus 4, 21, 24, 27, 28. 28 is even number. So some degrees of vertices theorem satisfied here. And also, total number of vertices are 7, and maximum degree of any vertex is only 6. That condition is satisfied. But can I say it is a simple connected graph? No, we cannot say immediately. We had to verify all possibilities now. Okay. Now, please understand this one very important point. According to rule number 2, please look at rule number 2. In a simple graph with n vertices, if 2 vertices are having degree n minus 1, then there does not exist a vertex whose degree is either 1 or 0. Clearly, in this example, in this example, there are 7 vertices are there. If there are 7 vertices are there, how can I find a vertex whose degree is 6? How can I find a vertex whose degree is 6? And again, sorry for the mistake, there are 7 vertices are there. If there are 7 vertices are there, and if 2 vertices having degree 6, then I cannot find a vertex of degree 1 by using rule number 2. Okay. So by using rule number 2, if 2 vertices having degree 6, if 2 vertices are having degree 6, then there does not exist a vertex of degree 5. Sorry for the mistake. There does not exist a degree. There does not exist a vertex whose degree is 1. Is it clear? So by using rule number 4, we can define, by using rule number 2, we can define like this. Okay, by using rule number 2. Right? Next, what about option D? So it is same as rule number 2 only. Rule number 2. See, there is a vertex which is having degree n minus 1. If one vertex is having degree n minus 1 means it is connected to remaining all other n minus 1 vertices. Then how it is possible to get degree 0? Is it possible? No. Okay. So it is also not possible. Repeating, if I find a vertex whose degree is n minus 1, it means that it is connected to all other vertices. Then I cannot find a vertex whose degree is 0. Therefore, I can eliminate it. Okay. So the explanation for this one is, if the vertex is having degree n minus 1, it is connected to remaining all other n minus 1 vertices. In such case, I cannot find a vertex whose degree is 0. Okay. Therefore, 4 options are eliminated. Now I want to verify, is it a graph or not? Means in a 5 vertices graph, there are 4 vertices of degree 3 and only 1 vertex of degree 2. Can you think and draw the graph which is similar to, which is satisfying the condition? There are 4 vertices of degree 3 and 1 vertex of degree 2. Okay, let me check. I'm taking 5 vertices graph. Okay. So with respect to this vertex, I want to draw a graph with degree 3. Right? So clearly this vertex is having, suppose let it be A. A is having degree 3. A is having degree 3. Like then how many vertices must have degree 3? 4 vertices must have degree 3. Okay. Now I'm taking B, but B degree is only 2, right? I want degree 3. Therefore, I can join these two. Okay, I can join these two. Now degree of B equal to 3. Now if you take it is C and it is a D, it is E. I want 2 more vertices of degree 3. So let me take C like this. Then what is the degree of C? Degree of C is equal to 3. Let me take this one. Degree of D is equals to 3. Now degree of E is equals to, yes, I can find this kind of graph like this. Okay. So this is a way you have to verify whether given degree sequence represents simple undirected graph or not. Okay. Right? But these 3 rules are most important rules. Okay. Next problem. Right. Which of the following degree sequence represents a simple undirected graph? A simple undirected graph. So you can do this problem in 3 different ways. One is by using plotting method. Means like whatever way I explained previous one, a degree sequence 2, 3, 3, 3, 3, 4 times. I explained the problem by using plotting points, right? That is one method. The second method is you can use four rules, whatever rules, or sorry, we can use three rules, whatever rules I explained in the previous example. Okay. And third one is you can use Havel-Acme result. You can use Havel-Acme result. Okay. You can also use Havel-Acme result. Now let me check Havel-Acme result for this problem. I hope you remember the Havel-Acme result, right? Okay. First, I want to see whether S1 is representing a graph or not. First, I will take S1. That is this analysis for S1. Like 6. So we have 4 times 6. 4, 3, 3, 0. In Havel-Acme result, first you have to cut the first degree. You have to cut the first degree and subtract 1 from 6 vertices degrees. 6 vertices degrees. Okay. Please watch that video which I explained Havel-Acme result. First cut the first one, that is 6. Now 0.6 6 degrees, 6 vertices degrees like this. Okay. From each and every degree, you have to subtract 1. By subtracting 1, 6 minus 1, that equal to 5. 6 minus 1, 5. 6 minus 1, 5. 4 minus 1, 3. 3 minus 1, 2. 3 minus 1, 2. And it is 0. Okay. After verify, are they in the decreasing order or not? Yes, they are in the decreasing order of vertices. They are in the decreasing order of vertices. Fine. Then again repeat this process. Again repeat this process. What is the first one? First one is 5. Simply cut it, and identify first 5 vertices degrees. Like it is first one, it is second one, third one, fourth one, fifth one. From each and every degree, you have to subtract 1. Subtract 1. 5 minus 1, which is 4. 5 minus 1, 4. 3 minus 1, 2. 2 minus 1, 1. 2 minus 1, 1. And it is 0. Okay. Now verify they are in the increasing order, decreasing order or not. Yes, they are already in the decreasing order. They are already in the decreasing order. Okay. Now again repeat the same process. Cut the first vertex degree, and identify 4 vertices degrees now. First one, second one, third one, fourth one. From each and every vertex degree, you have to subtract 1. 4 minus 1, that equals to 3. 2 minus 1, 1. 1 minus 1, 0. 1 minus 1, 0. And then it is also 0. Now tell me, is it simple graph? If it is a simple graph, suppose if it is simple graph, then the previous one is also simple graph. If it is simple graph, then previous one also simple graph. If it is simple graph, then previous one also simple graph. This is the way we are evaluating whether the sequence represents simple graph or not by using Havel-Acme result. In the previous video, I already explained the point. And please observe, there are 5 vertices are there. In 5 vertices graph, if one vertex is having degree 3, then we cannot find 3 vertices of degree 0. Okay, which is not possible. Not a graph. Okay, please understand there are 5 vertices. Let me draw 5 vertices. Otherwise, I can take 5 vertices. Now there is a vertex of degree 3. Let me take this vertex having degree 3. Vertex having degree 3. Then can you find a vertex of degree 0? Yes, I can find vertex of degree 0. Can you find vertex of degree 0? Another vertex? No, it is not possible. Can you find vertex of 0? No. Therefore, it is not a graph. Okay, so not a valid graph. Not a valid simple graph. Okay, so S1 is not correct. Now, what about S2? What about S2? Let me apply the same procedure for S2 also. So the explanation for S2. So first we can take 6, 5, again 5, 4, 3, 3, 2, 2, 2, right? Now identify the first vertex degree, that is 6. Simply cut that vertex degree and identify 6 degrees sequentially. Okay, and subtract 1 from each and every degree. Then 5 minus 1, which equals to 4. 5 minus 1, 4. 4 minus 1, 3, 3 minus 1, 2, 3 minus 1, 2, 2 minus 1, 1. Remaining 2, we can write as it is. Remaining 2, we can write as it is. Is it clear? It is Havel-Ekman result, which we already discussed in the previous video. Therefore, I'm directly solving the problem. But tell me, are they in the decreasing order? No, they are not in the decreasing order. Therefore, again, arrange the decreasing order. Okay. So by arrange the decreasing order, 4, 4, 3, 2, 2, again 2, 2, 1, which is decreasing order. Okay. So after arranging decreasing order, now cut first one, that is 4. Identify 4 immediate vertices degrees. 4 immediate vertices degrees. And from those, you have to subtract 1. So 4 minus 1, 3, 3 minus 1, 2, 2 minus 1, 1, 2 minus 1, 1. The rest of the elements are same. Sorry, 1. Okay. After subtracting, verify, are they in the decreasing order or not? No, they are not in the decreasing order. Therefore, again arrange in the decreasing order. That is 3, 2, 2, 2, 1, 1, 1. This is a decreasing order. Okay. Now repeat the same process. I can say it is a decreasing order. Please remember. Okay. Here I can say it is a decreasing order. Now cut the first degree, and identify 3 vertices having degree 2 like this, and subtract 1 from each and every degree. Then 2 minus 1, 1, 2 minus 1, 1, 2 minus 1, 1. Remaining are 1, 1 only. Okay. Can you find a simple graph which is having, can you find a simple graph where each and every vertex having degree 1? Yes, I can find. The graph may be looking like this. I have a simple graph with 6 vertices, and each and every vertex having degree 1. Therefore, S2 is a valid sequence of simple undirected graph. Therefore, I can say only S2 is a correct answer. Right? Okay. So in this problem, we applied Havel-Ekman result for finding answer. Right? In the next video, I'll discuss few more particular example based on the concept of sum degrees of vertices theorem. Okay. Thanks for watching this video.